Ever wondered how AI masters tasks like recognizing images, translating languages, or even playing chess? It all starts with neural networks, complex systems that learn by adjusting millions of parameters. But here's the catch. Training them is like navigating a maze with no clear path. Traditional methods like stochastic gradient descent often stumble, taking too long or getting stuck in dead ends. Today, we're diving into a breakthrough that's changing the game. A new approach called SAMT, which makes neural networks learn smarter, not just faster. Let's break it down. Neural networks are like layered puzzles. Each layer has its own set of weights. Think of them as knobs that adjust the model's predictions. Traditionally, training updates all these knobs at once, like trying to fix a broken machine by twisting every screw simultaneously. It's messy, inefficient, and prone to errors. Enter SAMT, Stochastic Alternating Minimization with Trainable Step Sizes. Here's the twist. Instead of juggling all the knobs at once, SAMT tackles them one layer at a time. Imagine solving a jigsaw puzzle by focusing on one piece, then the next, rather than scrambling all pieces together. This alternating approach reduces computational clutter and keeps training more stable. But here's where it gets even cooler. SAMT doesn't just update weights, it learns how to update them. Traditional methods use a fixed step size for adjustments, like driving at the same speed no matter the road. SAMT, however, uses meta-learning to adapt its step size dynamically. It's like having a GPS that adjusts your speed based on traffic, road conditions, or even your destination. Whether it's a single number, a row of numbers, or a whole matrix, the step size evolves to fit the task. Why does this matter? Think of it as giving the model a toolkit instead of a one-size-fits-all hammer. In experiments, SAMT outperformed existing methods by achieving better accuracy with fewer updates. It's like learning a new skill. Instead of practicing every move blindly, you tweak your approach based on what works, saving time and effort. The math behind it. Researchers proved SAMT converges reliably, even in the chaotic world of non-convex optimization. But you don't need to crunch numbers to see the impact. From image recognition to natural language processing, SAMT's flexibility and efficiency could speed up AI development, making systems smarter and more adaptable. Now let's dig into the experiments. Researchers tested SAMT on datasets like CIFAR-10 and CIFAR-100, digital photo libraries with thousands of images. Initially, SAMT lagged behind competitors like Adam and SGD, but here's the twist. As training continued, it not only stabilized but surpassed them. The loss curves, which track how far off the model is from the correct answer, showed a smoother, more reliable path. It's like a runner who starts slow, but finds their rhythm and finishes strong. What makes SAMT special? It's not just about speed. This method adapts. In complex data, like high-resolution images or massive datasets, it learns better step sizes on its own. Think of it like a chef tasting a dish and adjusting the spices mid-recipe, rather than following a rigid formula. This flexibility lets it handle tricky scenarios where other methods might stumble. Here's another cool part. SAMT is less picky about its starting settings. Imagine tuning a car's engine. Too much gas and it stalls, too little and it's sluggish. SAMT handles this gracefully. Even when researchers tweaked its initial parameters, it stayed steady, except in rare cases with super large networks. That's a big deal because it means the method is more reliable in real-world applications. So what does this mean for the future? SAMT isn't just another tweak. It's a smarter, more adaptable approach that thrives as problems get complex. And the best part? This is just the beginning. Scientists are already exploring how SAMT can fine-tune itself even further, making AI more efficient and powerful. But here's the deeper insight. This research also reveals how errors in AI learning don't just shrink, they vanish at an accelerating rate. Let's unpack that. In machine learning, models make guesses, and errors measure how far off those guesses are. This study shows that under the right conditions, these errors don't just get smaller. They accelerate their decline, like a ball rolling down a hill, getting faster and faster until it hits the ground. But here's the twist. It never actually reaches zero. Why? Because real-world data is messy. There's always some noise, like static on a radio. The error settles into a tiny, stable value, like a ball balancing at the bottom of a valley. How did they prove this? The team started with a complex equation, describing how errors change over time. They broke it into two parts, PT, a decay factor that shrinks errors, and ST, a measure of noise. Think of PT as a rubber band pulling the error tighter and tighter, while ST is the tiny vibrations that keep it from ever fully disappearing. The real magic happened when they used mathematical induction, a technique that's like stacking building blocks. Each step relies on the one before it, proving that errors can't spiral out of control. It's like showing that if a bridge's first plank is sturdy, and each new plank is added safely, the whole structure will hold. And the proof? It's not just theory. The researchers tested their ideas on KMNIST, a dataset of Japanese symbols. The results? Algorithms like SAMT and SAMTS stayed stable while learning, matching their mathematical predictions. It's like watching a recipe work perfectly every time, whether you're baking a cake or training an AI. So why does this matter? This discovery gives engineers a blueprint for creating algorithms that learn faster and more reliably. Imagine self-driving cars that adapt to sudden weather changes or medical AI that spots rare diseases with pinpoint accuracy. The math here is the invisible engine powering those breakthroughs. Next time you see AI doing something amazing, remember, it's not just raw power. It's clever math, like this exponential error reduction, making the impossible possible. Thanks for watching. Stay curious and let me know in the comments. What's one AI mystery you'd love to see solved? Let's keep exploring together.